on the screen, which is a piezoelectric sensor. And you see this has an input here on the ground, and we want to use the voltage on this side to relate this input, the acceleration, to the voltage over here. That relationship is going to be done through a transfer function. So how do we actually do this, and what does that mean? So that's the subject of what I'm going to be talking to you about now. Let's just start simple here. Um, you have a situation where we we have on the left hand side, you have this you move it a little bit. Over here we have a, right here we have an input, okay, and we have, of course, on this other side we have the output, over here. We need to measure the voltage over here to be able to relate to this input, as I mentioned a moment ago. So we could put here like a step input and find out what this is, but we are going to take a whole different route right now. We're going to enter a sinusoidal input in here, and deliberately, maybe with a frequency of 1 hertz, and see what happens over here. And then we're going to change to 2 hertz. What happens over here? 5 hertz, 10 hertz. What happens over here? And then we go 1,000, 10,000 hertz, and see what the response is. So for every frequency that we have on the input in here, we get a plot of the response of the frequency as well as the amplitude. So what I'm trying to say is, over here we could say, okay, the input is going to be a function like this. It's going to be a function like that. And the one over here, this on this side, the output, if the input is a function, the output also is a function. But you may notice, and I'm deliberately drawing it in here, a little different. There's some difference between this one here, between what we have done on this and what we are doing over here. Can you tell what it is? My drawing is not perfect, but I mean, can you see a difference?
Sine and cosine.
Okay, I think what he's trying to say is that, you see, this looks more like a sine curve. This one looks like a cosine curve, right? What's the difference between those two? No, it's just one is 90 degrees out of phase, right? Yeah, okay, everybody knows that. So what I'm going to suggest here is that if there is a difference in the frequency with which we see the output, we are going to call it that the phase angle. Okay, so if I draw both of them in one plot, hopefully I can do a good job. Let me try to see if I can do this. This one, let's see, the first one might be like this, yeah? But the second one, I need to change pens here. And I'm going to do it with the red pen. That one, if it is 90 degrees out of phase, you're going to have this. And the difference here, this difference in here, this is going to be phi, and we're going to call it the phase angle. So what is the phase angle? Now that I have said this, it is the difference with which the output tracks the input. And if both of them are in phase, then fine. You know, there's perfect control if everything is all in phase. But there's another thing in here. I am going to make a plot for every frequency that I put in on this side. For every frequency that I put on this side, I want to record the amplitude of the signal and also the phase angle. Okay? And I need to do that in a certain way. I need to do a different plot in here. Maybe I'll just do my plot over here so that we don't have to go to a different page. In here, I am going to say on this plot, let's say I put this is 10 to the 0 hertz. This may be 10. This would be 10 square, 10 to the third, 10 to the fourth, 10 to the fifth, and 10 to the sixth. Yeah? And in here, I am going to plot the value of the voltage, let's say, the magnitude of it. But underneath, on the same plot, you may say, same scale that I show you here, 10 to the 0 and 10 and 10 to the fourth and 10 to the, this was the third, no, this was second, 3, 10 to the fourth, and then finally 10 to the sixth. I am going to plot phi. Okay? So the way this works is, on this one, I may have a plot that goes something like this. Sort of like the shape of the way you're going to get your response in here. What does this actually mean? It means that the amplitude increased. Remember, this is a ratio between the output and the input. But in here, it didn't increase anymore. It means that in here, this is 1. That the input equals the output. So if the output tracks the input, then this has a perfect control. So, and in here you might have a plot that relates to the angle. But let's just analyze. This is the on this axis is the frequency. Yeah, and in here is the magnitude. And of course, this one is the phase. See? So whatever plot I have of this in the shape that it takes, this is going to be the angle. Okay, so if we could switch for a moment to the other picture here, and I'll show you this. This was I'll show you what I mean. All right, this is the bond graph model of the circuit, which we went over last time. This is the bond graph model of the in detail, so that the same variables that are used in the bond graphs relate to the ones using a block diagram. And so you can see this is the method is equivalent. This one was the model of the transformation over here, which is in here. And finally, the other thing was the mechanical side will produce in short a bone graft model like this, but we can reduce it to one like this, see? Because these are through power, yeah, so in here, and then you can put it together like this, see? This is in fact how it should look. You have in here the mechanical side, the piezoelectric transformation, and the electrical side. So in practical terms, we need the voltage like E12 in here compared to this one here, E1. See, that's what we need. We need this E1 over here compared to the voltage of E12 over here. So that relationship between this voltage and this input over here, that relationship is called the transfer function. And that transfer function, once you have the bone graft model in CAMG and you specify what the output is, the file CAMG SYM will derive the transfer function for you. Okay? And so if you do that, you are going to get, if you put this into CAMG, you're going to get this output. You're going to get, these are the, you know, we have two sources. We have this one and this one, but this one is just to represent the operational amplifier. These are the state variable vector, the A matrix, the B, the C, and the D matrix. This is the characteristic polynomial, which is the denominator of the transfer function. And here reveals that the computer has in fact derived this transfer function. Okay, so now you see these are much better plots than what I had a moment ago. The one that I had is sort of like this in yeah, right here. See? I was trying to explain you how this plot would go, and this one here may go like this. See? Both of these, you say both plots equal body plots. Yeah? So on a body plot, you always get the amplitude plot and you also get the phase plot. And that you can see it in a much nicer way on this picture, because what you have in here is the you see at 1 hertz the input and the output are the same. Up when it hits a little bit after 10,000 hertz, the amplitude goes up and then comes down. What does this mean? This means that in this place, in this area like this, the sensor is perfectly okay. But if you operate that sensor between these frequencies or over here, your output does not track the input, and it behaves wrongly. So your sensor is only good between 1 and about 10,000 hertz. After that, it doesn't work at all. I mean, It is not the way we want it. And the phase angle also has the same conclusion. You see the input and the output are exactly on the same phase. So no phase angle. But here is if the phase angle is in degrees or radians. How many degrees one radian?
57 point.
No. One circumference is 2 pi radians, right? So divide so you'll divide the you convert degrees to radians. 360 divided by 2 pi.
1 radian equals 57.
57 point something degrees. Exactly. That's what it is. So so in here, both of these are the body plot. Both of those make up the body plot. But what I'm trying to say is that in here you have the on this side, all right, on this side you have, like I said, this is the magnitude plot. Do you see? I wrote it there, magnitude in there. And this is the phase plot. This is the phase plot. But what happens now is that you have in fact produced here the body plots. All right. But this one, if I test the system with the step response, this is the step response of the system. Or if I test it with an impulse response, this is what it is. So the question now is, how do I get these body plots? And how do I get this step and impulse response? So this one was the impulse response. Yeah. So what we need to do is to get the plot on the get the bond graph model on the screen, and then get the and then let's get on doing the obtaining the transfer function, and as we have explained here, our objective would be next to just give an example of different example here, and let's obtain the transfer function, the body plots, and there's one more plot that I need to explain to you called the root locus plot that basically comes as for free. Once we do the setup, the computer will calculate not only the body plots but also the root locus plots. So let's just go and do that next.